What if we have three concurrent forces in equilibrium? When a body is in equilibrium under the action of three concurrent forces, the problem can be solved by drawing a free body diagram of the point through which all three forces pass and constructing a force triangle. The completed force triangle should satisfy the conditions defined by our rule for vector addition. Vectors must be added in a tail-to-tip fashion for equilibrium to exist, and the resultant must always equal 0. This is only true if the vector addition begins and ends at the same point. The force triangle must form a closed figure. In example 3.4, a crate weighing 6,000 newtons is suspended from two cables as shown in figure A. For part A, draw a free body diagram of point B. For part B, construct a force triangle that satisfies the conditions for equilibrium of point B. For part C, use your force triangle to find the tensions required in cables AB and BC. For the solution, the appropriate free body diagram is shown in figure B. Note that the force FAB and FBC are assumed to be in the directions shown. Their actual directions will be verified by the force triangle of part B. We begin our force triangle by drawing the known weight of 6,000 newtons in a downward direction. Through one end of this vector, we construct a line that is in the same direction as FAB, extending the line indefinitely in both directions. Through the other end of our known vector, we draw a line in the same direction as FBC, extending this line indefinitely in both directions. These constructions are shown in figure 12a. Note that our weight vector and the two drawn lines form a closed figure, thus ensuring a 0 resultant. By drawing arrowheads in the required tail-to-tip fashion of figure 12b, we can verify that the directions of FAB upward to the left and FBC upward to the right agree with the directions assumed on our free body diagram. As shown in figure 13a and b, these same results would have been obtained if the lines parallel to FAB and FBC had been drawn at opposite ends of the weight vector. We use the laws of trigonometry, or the laws of sines, to find the missing forces. For force FAB, the equation is 6,000 newtons divided by sine of 60 degrees equals FAB divided by sine of 70 degrees. Force AB equals 6,510 newtons. For force FBC, the equation is 6,000 newtons divided by sine of 60 degrees equals FAB divided by sine of 50 degrees. Force BC equals 5,307 newtons. This problem contained two unknowns, FAB and FBC. If a third supporting cable, BD, were added as shown in figure 3.14a, a third unknown, FBD, would be introduced. The resulting vector addition would yield a force polygon similar to that of figure 3.14b. Although this construction shows a specific combination of values for FAB, FBC, and FBD, which form the closed figure ABCD, different force combinations forming the polygons would be equally valid. No matter which combination is selected, however, there is insufficient information to solve for any numerical values of force. Such a problem contains too many unknowns and is said to be statistically indeterminate. Let's look at an example. The three forces acting at point A in figure 3.20a are in equilibrium. The magnitude and direction of F1 and F2 are known. Determine F3. First, Draw all the known forces you have. The first known force is T equals 5 kip. Through the end of T, draw a line parallel to FBC, and through the other end of T, draw a line parallel to FAB. Two possibilities exist, as shown in Figure 3.20a and b. In either case, the lines of action intersect to form a triangle. The force triangle can now be constructed around either of these triangles, Figure A and B. Using the graphical method, select the scale. Draw F1 from A to B and F2 from B to C. Force F3 must be represented by a vector drawn from C to A, Figure B. Measuring the magnitude and direction of F3, we have F3 will yield 8 kilonewtons with an angle of 54 degrees. Using the mathematical method, a force triangle is constructed in Figure C. Angle B equals 90 degrees plus 20 degrees yields 110 degrees. We use the law of cosines. F3 squared equals F1 squared plus F2 squared. Minus 2 times F1 times F2 times the cosine of angle B. So, we have 5 squared plus 4.8 squared minus 2 times 5 times 4.8 times the cosine of 110 degrees, which equals 64.46. Then we obtain F3, which equals 8.03 kilonewtons. Now we can use the law of sines to obtain a value for the angle C. Sine C equals 5 divided by 8.03 times sine of 110 degrees equals 0.5851. C equals 35.8 degrees. The angle theta 3 equals 90 degrees minus C equals 90 degrees minus 35.8, which equals 54.2 degrees. F3 equals 8.03 kilonewtons at an angle of 54.2 degrees.